Hello, my dear students. Warm welcome to all of you. We are with physics now. Okay, we'll be talking very seriously about physics now. Okay, myself is Dr. Shobboshachi Shen. I'll be offering you the physics courses, course objective, course outcome. You can see on the screen, and we are in outcome-based education. So every course is mapped with what is its probable outcomes, which I have illustrated later on. Now there are five modules. Now we'll be adapting one by one to each module and explore the world of physics. Now let us explore what is the topic of the day. You should keep one thing in mind, that whatever we teach in these classes, each video lecture is basically a building block of your future engineering courses. Each class is going to give you some fundamentals, some new concept. And if you add all those concepts at the end of the semester, you will get the correct path of entering into your own engineering curriculum, because all your curriculum are essentially the application of physics. Engineering means physics applications. So let us explore it a bit more. The class 26 of my physics 1 courses. Today we'll be talking about the most important topic in respect of the studies of semiconductors, popularly known as the solid state physics. Solid state physics is a vast branch of physics. It's a, we do take it as a physics student have to learn a lot about solid state physics. It may be the physics of semiconductors, it may be physics of solid itself. Now it is popularly called condensed matter physics. It's a sea of knowledge, I should say. And being an engineering student in the very first semester, you will be only introduced with some very basic fundamental knowledge. It is almost like only, if you think English alphabets, it's only like knowing like A, B, C, D, E. You don't have to learn the remaining. Okay, only five alphabets you have to know. So it is basic, very much, very, very easy, simple topics, some fundamentals of solid state physics will be shared with you. Or in a better language, these things are also called crystallography, okay, separately. Okay, so these things are actually taught under solid state physics, that is how a solid is made of, uh, what are the various possible ways the atoms can form a solid, or whether how a solid is made of, that structure is basically called crystal structure, and who makes the crystal structure. Initially it's all geometric idea. Okay, so from geometric idea to we'll get into the actual molecular system. Molecules are atoms actually replacing the coming into the picture, making actual solid. Variety of structures, uh, from in case of some popular material like iron, copper. Okay, how their structure changes. Okay, and most importantly is that in the study of semiconductors. Okay, in the part 2 next year, some of your friends will be learning about energy bands. Okay, so that talks about how electron flows through a solid. Okay, so all those things you can only learn, okay, if you have got your fundamentals right. So that is what we are trying to do. We are trying to develop basic fundamental, basic ABCD of solid state physics in this class. Okay. So it's very easy. Just get a tool. This is the 26th class in a row, as I mentioned. This is me. You can always contact me in those numbers. And this is very, very elementary, which all of you know. Matter can be solid, can be liquid, can be gaseous. There is a fourth state also called plasma, which is the mixture of ions. The solid, what is the speciality of the solid? Solids are of different size and shape. Solids have got different volume. Solids have got different mass. And if they are static, they don't have any momentum. If they move, they should have some definite momentum also. What is the property of liquid? Liquid don't have any size, definite size or definite shape. It takes the shape of where it is placed basically. A liquid has got a definite volume, okay, like just like solids. Okay, and the other one is a gaseous system. A gas has got no size, no shape, but it is defined with some amount of the volume is there. Okay, it is incorrectly written there. A gas maintains a different volume. Okay, no size, no shape, but it comes up with different volume. Okay, it has finite volume. Okay, so finite volume will be there for the gaseous system. So these are the classification between the solid, liquid, and gaseous system. We only talk about the solid materials which are having that much of quality. Okay, they are of definite size and shape. Now, question is that who gives them the size and shape? So that question we can answer actually. You see, most of the solids actually, majority of the solids, okay, are crystalline in nature. Okay, so what is crystalline? That is to be clarified. And some of the solids are amorphous. Okay, amorphous are there. Okay, so the first class is crystalline solid, and the second type of solid is the amorphous solid. So this is the case one, crystalline, and the amorphous. So these are the two classifications of the solid materials. Okay, liquid and gas. I am not focusing on that now. What is a crystalline solid? In a crystalline solid, atoms do or molecules are arranged in a proper way. Because a solid, crystalline solid is a very definite size and shape. So to make a crystalline solid, the atoms or molecules, if it is an atomic crystal, then atom molecules is molecular crystal. Atoms or molecules, okay, are arranged in a regular periodic manner. Okay, as you can see there. Okay, you see there is a definite periodicity. These red balls are or atoms are repeated after a definite gap. These blues are also repeated after a definite gap. Okay. Whatever will be the way, this direction or the horizontal direction, they are arranged in a definite way. Okay. So these are the examples of crystalline solid. What is the specialty of crystalline solid? They have got definite size and shape. So atoms making a crystalline solid are also placed in a definite position. Okay. There are some examples you can see there. And ultimately this is the solid. Okay. Same thing. Okay, these are the crystalline solids. Examples are there given there: sugar, table salt, sand, snow. Okay, so these type of these are the basically examples of the crystalline solid. Okay, now the some more examples of crystalline solid. Ice itself, the diamond. Diamond is crystalline. Iron is there also. Okay, and table salt is the other example. You see, crystalline solids, there are three classes, okay, three types. One is like diamond, okay, who is only made of like carbons. Okay. But if you look at the other two, sodium chloride is a molecular. Uh, you see how it is made of. It's a ionic structure is there. Okay, Na plus and Cl minus. Cl minus is this green balls, and Na plus is this dark dark ball. That is gray colored balls. Okay, so this is the way they are placed. You can see they are arranged in a. You see, green is repeated after a definite cap. Here also, green is repeated after a definite cap. They are arranged in a definite periodic way, as you can see there. Okay, and making the structure of sodium chloride. Okay, and making a sodium chloride structure. Last one is the structure of ice. You see, water molecules are there. Okay, these are all water molecules. You can see there, these are the water molecules. Okay, so there is a structure of ice, sodium chloride, and diamond. Okay, you can realize also. Okay, this is for ice. You see, there is these are arranged after a definite gap. Okay, definite arrangement is there. So, what are the three types of crystalline solids? One is like diamond, okay, that you can see. Another is like sodium chloride, okay, Na plus and Cl minus will be there. And water is also there, okay. Water is the polar molecule according to the studies of dielectrics. But here, water, you see, is connected with hydrogen molecules, etc. This is on water. Okay. This is the water. These are the region. Okay. But the key is that definite way everything is arranged. Okay. So these are the various classes of crystalline solid. Molecular crystal, the sodium chloride is an example of that. Ionic crystal, there is also Na plus Cl minus is there. Nectar crystal and metallic crystal. Metallic crystal means uh, they do make metals. Okay. For molecular crystal means polar, non-polar, or hydrogen bonded. Okay. So now if you see, this is the amorphous structure. So after crystalline, we can move into amorphous. As I mentioned, for amorphous, you do not get similar thing as you anticipated. Okay, because not is nothing. There is no regular periodic arrangement. Okay, so they do not have any very. They're all randomly oriented. Okay, composed of. There is no definite arrangement. So randomly oriented ions and atoms makes this type of amorphous crystal, and they are for uh, crystalline material. The order parameter remains valid for over a long distance. Okay, but here for amorphous materials, this ordered arrangement is only valid up to 3 atomic lengths. Okay, the examples of mainly is amorphous that is it does not have a definite regular arrangement. Okay, that's amorphous. Example amorphous silicon, plastic, glass, everything is there. Okay, some examples of amorphous material. You see how it is changing. The very popular example is given. Okay, I do not know whether you can realize here in this picture, but this is a very good picture. It's all arranged in an irregular manner, and you see there is no regularity, no periodicity. So the best examples that could be given is like this. Okay, all of us have experienced cotton candy. Okay, once in a life, or maybe more than one. So there we came to know. Okay, here the difference between amorphous and uh, the difference between crystalline and amorphous system. Amorphous have got no regular pattern of ions and molecules, but crystalline do have regular pattern of arrangement of atoms and arrangements of solids, regular arrangement of ions and molecules. The amorphous material the first point is this regular arrangement in crystalline system, regular arrangement, and amorphous system it is lost. Okay, you can see the example of silicon dioxide, the glass material, it is regular arrangement and it is okay, which is amorphous, and the quartz crystal, which is also made of glass, but you can see that this is regular. Okay, left hand side. These so crystalline materials have a defined melting point and melt over a range of temperature. Okay, no definite heat fusion in our system, and crystalline systems have got definite heat fusion. Okay. So for crystalline material, everything is defined. Okay. It is structure is regular, melting point is definite, heat fusion is definite. Okay, so all these are good points. Okay, now let us focus particularly on some of the crystalline solids. You please see how it is made of. Okay, okay, please see how it is made of. Okay, first of all, you can see. Suppose I choose a point here, that red ball. So suppose this point is repeated in the x direction after a gap of a. So if they keep on repeating, they'll be making this structure along x direction. Similarly, if they keep on repeating in the y direction, so this is once they disperse, but ultimately, you see, it will be repeated along y direction. So what you notice, there is a definite periodic arrangement of atoms or molecules or even for these points to make a crystal lattice. Okay, you can see there, here A is the lattice constant, B is the lattice constant along y direction, and this is a plot of the 2D view of the whole situation. If we add it, make a 3D plot, that will give a 3D view. But you can see there what is lattice point, what is lattice constant, I just repeat the story. You see the right hand side four arrows that will define the lattice constant. Okay, so these are the lattice points. Each point, each red ball is a lattice point, and they are making repeated along x direction and ultimately forms the entire crystal lattice. Okay, along x, and they can repeat in the z direction also, which have not deliberately mentioned. Okay, so basically, you see, so now what is space lattice? Because a lattice is basically how you are placing the ions on atoms. Okay. Now the automatic question comes in: what is a space lattice? Space lattice is a distribution of points in three-dimensional space in which every point has identical surroundings. Okay, that is an infinite array of points in three dimensions in which every point has surrounding identical. You see, there is a definite difference between atoms. Every point has got its identical surrounding, that is, in an infinite array of points in three dimensions, in which every point has surroundings identical to every other point in the array. The array is an infinite element of points in general. That is a basic definition of array. Okay. Now up to this picture, you see uh, those red balls are basically indicating the lattice points along x direction. Green balls, okay, I'm talking about only one line, the leftmost refers to the repetition in the z direction. Okay. Now that red box, okay, you see this red box coming out is called a unit cell. Okay. So this is the unit cell. Okay, this is the unit cell. Okay, this is the unit cell. This is the unit cell. Okay. Now it's repeated along x direction. You can see the repeated in the y direction like this. Okay. Now come to the definition of unit cell. Unit cell is the smallest basic unit. Okay. Because everything is 3D now. Okay. So that is the unit cell. Unit cell is the key. It is being repeated in space along its direction and in the perpendicular direction. Okay. Perpendicular direction means z direction, and ultimately, if they are repeated in all 3D, you'll have the lattice form. I hope I have made it clear to you. Now, this is a unit cell. So, what is a unit cell? It is the smallest unit. If it is repeated in space, so say it is repeated in x direction, it can repeat along this direction, it can repeat along this direction, it can repeat along this direction. Okay, now please see unit cell is there. Okay, these are unit cell. These are the lattice points. Okay, so the idea is that this will be repeated along x. Okay, anybody can see this unit cell in 3D. Earlier I was showing in the 2D view. Now this is a 3D view. Okay, and this will keep on repeating along this direction, and you can see there in the perpendicular direction also in the actual crystal. So now in unit cell, you see few points to be noted here. If I consider this point as origin, here in this picture, A, B, C are the three lengths of this unit cell, and alpha, beta, gamma are the three angles. Okay, just like alpha is the angle between B and C. Okay, okay, and the three angles are alpha, beta, gamma. If you can understand, this is beta, this is alpha, and these are the three angles. So this quite explain, you can see and understand. In some time it is also written like this one. Suppose this is your unit cell. If this has to unit cell, relevant series, okay, this is the origin. So this x perpendicular direction is y, and your third direction is z direction, and the angle made, say with the x direction, the angle will be alpha. If the y direction, x angle is alpha, yz angle may be beta, and zx angle may be, sorry, xz angle, this angle may be something like say gamma, as it is shown there. Shown there, you can see. Okay. alpha, beta, and gamma. And the suitable choice of these six variables are there. A, B, C are the three length variable, and alpha, beta, gamma are the three angular data. Suitable combination of this ABC, alpha, beta, gamma actually divides the crystals into variety of structure. Variety of crystals are there. 7 primitive and 14 Bravais studies are there. We'll discuss them. Okay. Primitive unit cell is determined. 27 is this one is basically this is the primitive unit cell at the top. Okay, it's determined by the parallelepiped formed by the, you can see this is a primitive unit cell. This is the three vectors, A1, A2, A3. Okay, and this is the smallest unit basically. Okay, you can see there. This is the primitive unit cell. Interestingly, for example, this is simple cubic crystal. Interestingly, at the center there is no atom at all, which is also the observed expectation in case of simple cubic crystal. Now you can further write down. These are the primitive and conventional unit cell concept. Single crystal. You see, this is an SCC structure. So this is a orange arrangement. The other one is that more than one lattice point per unit cell. They are integral multiple of primitive volumes. All these things you can see there. Okay. A primitive unit cell, I just told you a few minutes back. You can see there more than one lattice point. Now, primitive unit cells have got only one lattice point effectively, and if there is more than one, actually they are called the non-primitive unit cell. Actually, there are 7 primitive unit cells. Beyond that, everything is actually beyond that variety of 14 regularities will come up in our discussion. Okay. So, what is the effective number of atoms in a unit cell? Those calculations are also needed there. Okay. Yeah, this there is only one atom. Okay, no problem. But if there are if the number of atoms, okay, is the non-primitive units. Primitive and conventional cells different. You can see that I told you just now. This primitive cell, simple cubic crystal, and conventional cell is body centered cubic crystal. Okay. Now, in a crystal structure, what happens? Those points that I've shown you, they are called lattice point. Okay. And when these lattice points are added with the atoms, actually, we form a basis. So let us see how it is forming. Okay. So this is the formation of basis. Now how it is, you see, these are all lattice points now. But lattice point is a geometric concept. You add a copper atom there, okay? If you add it, you see you're adding atom or molecule, in this case atom, you can see at the top to the lattice point. Then one atom or molecule to the lattice point plus lattice point, this will be one basis point, okay? Okay, I just show you. Suppose coppers are occupying the position, you see. You can realize, okay. So this is the concept of basis. Now today here I'm stopping here because many more new concepts need to be shared. I'll talk about my next agenda is to talk about the Bravis lattice. Okay, variety of units. So 7 basic unit cells are there, and then 14 more will come. We'll discuss that in the next.
You and me were meant to be in the great outdoors, forever free. You and me meant to be in the great outdoors, forever free. Like a bird on a tree, I'm just sitting here. I got time, it's clear to see. From up here, the world seems small. We can sit together, it's so beautiful. You and me, we meant to be in the great outdoors, forever free. Sometimes you need to go and take a step back to see the truth around you. From a distance you can tell